Before we start our work on the theorems of a circle, we will take a quick review of the various parts of the circle. We can form a circle by rotating a compass through a fixed point. The point of rotation forms the center of the circle, and the circle drawn by the line forms the circumference of the circle. To find the area of a circle, we use the formula A equals pi r squared, where pi is usually taken as 22/7 or 3.14, and r is the radius of the circle. The length of the circumference of the circle can be calculated by using the formula c equals 2 pi r, or c equals pi d. Any line passing through the center of the circle and touching the circumference is known as the diameter of the circle, and any line touching the circumference but not passing through the center of the circle is called a chord. And a chord splits the circle into two segments, a major segment and a minor segment. A line between the center of the circle and the circumference is known as the radius, and a radius is always half the length of the diameter. The plural of radius is radii, and the area between two radii is known as a sector, and the area of a sector is calculated by using the formula pi r squared multiplied by y divided by 360. The region where a sector touches the circumference is referred to as an arc, and the length of an arc is found by using the formula 2 pi r multiplied by y divided by 360. It is important you do not confuse these two formulae. Angles at the circumference formed at the same arc are equal. In this example, angles C and D are equal because they are formed on the same arc of AB. When we draw lines from both ends of a diameter to the circumference of a circle, the angles formed at the circumference is always 90 degrees. Sometimes we have to prove this theorem, and we do so by drawing another line from the center of the circle to split the angle at the circumference. We have now formed two triangles, and because two sides of each triangle are equal, these triangles form two isosceles triangles. And because these triangles are isosceles triangles, the angles formed at x are equal, and the angles formed at y are equal. All these angles form the angles of our original triangle, so all these angles must add up to 180 degrees. Therefore x plus y equals 180 degrees. Another way of expressing this would be 2 upon x plus y equals 180 degrees. Now if we divide this expression by 2, we find that x plus y equals 90 degrees. By finding the size of these two angles, we have also found the size of the angle in our original triangle. Therefore we have proven the theorem that the angle in a semicircle is 90 degrees is true. A tangent is a line that touches a circle, and at the point where a tangent and the radius of a circle meet is always 90 degrees. Furthermore, two tangents constructed from the same point outside the circle are the same length between the point of construction and where they touch the circle. So in this example, line AB is the same length as line AC. The angle at the center of a circle is always twice the size of the angle at the circumference, provided the lines originated from the same points. If the angle at the circumference is x, then the angle at the center would be 2x. Sometimes we have to prove this theorem. In doing so, lines DC and CD are equal because they are both radii of a circle. If we now draw another radius between the points C and A, we form two isosceles triangles, with both angles x being equal and both angles y being equal. Since we know all the angles in a triangle add up to 180 degrees, we can say angle DCA equals 180 minus 2x, and that angle BCA equals 180 minus 2y. We also know that where lines meet at a point, such as at point C, all the angles total 360 degrees. Therefore, angle DCB equals 360 minus angle DCA minus angle BCA. So by substituting the values we have already found for angles DCA and BCA, we can write this as angle DCB equals 360 minus 180 minus 2x minus 180 minus 2y. If we simplify this further, this becomes angle DCB equals 2x minus 2y. Or angle DCB equals 2 upon x plus y, which is the same as saying angle DCB is equivalent to twice the angle DAB, therefore proving the theorem. In the alternative segment theorem, angles x are equal and angles y are equal, and as with all circle theorems, we may be asked to prove this is true. To do this, we use our knowledge of the facts of related angles. We have already seen a tangent forms an angle of 90 degrees with the radius of a circle. Therefore angle CAD plus x equals 90 degrees. Angle ADB is an angle in a semicircle, so this angle is 90 degrees. We also know all the angles in a triangle add up to 180 degrees, so angle ADB plus CAD plus y must equal 180 degrees. We know angle ADB is 90 degrees, so we can write this as 90 plus CAD plus y equals 180 degrees. Or CAD plus y equals 180 minus 90, or CAD plus y equals 90. But we've already calculated angle CAD plus x equals 90 degrees, so therefore angle x and angle y must be the same, thereby proving the theorem is true. This shape inside a circle forms a cyclic quadrilateral, and is formed when each corner of the quadrilaterals touches the circumference. The opposite angles of a cyclic quadrilateral add up to 180 degrees, so P plus Q equals 180 degrees, and R plus S equals 180 degrees. So these are all our circle theorems. You must not only be aware of the theorems, but of how the theorems can be proven.